So just like a hydrodynamic entry region, you can also have a thermal entry region, because think about it. So we talk about hydrodynamic boundary layer, thermal boundary layer, and concentration boundary layer. So, and we know that unless the Prandtl number is 1, the hydrodynamic boundary layer is different from the thermal boundary layer. So that means there will be another entry length. So this is called thermal entrance region, where basically two of the thermal boundary layer merges, and this is going to be called fully developed for thermal. T indicates for the thermal, and the criteria is basically 0.05 multiplied by Reynolds number multiplied by Prandtl number, and diameter is the diameter of the pipe. Okay, so this is how we calculate the thermal entrance region. So we have hydrodynamic entrance region, thermal entrance region. Unless Prandtl number is 1, they are different from each other. Okay, and if you have a turbulent flow, so the thermal entrance region is basically 10 times the diameter of the pipe. Okay, so this is fairly straightforward. And again, just like in the case of velocity, so the temperature can also be the radial dependence of temperature can also be idealized. So you can basically integrate the temperature across the cross-section area and divide it by the cross-section area, and then you get an idealized temperature profile. So this is going to be Cp times T times rho times Um times 2 pi r square dr, and this is divided by mCp. So if you do that, so this is, you get so dmCp integrated over the temperature divided by mCp will give you the mean temperature. Energy balance. So now let's do the energy balance for this system. So let's say we have a fluid that is at TMI, at inlet temperature, and it leaves out of the system at outlet temperature. Let's say the mass flow rate is the same, Cp is the same, and if you want to calculate how much of heat the system takes going from TMI to TMO, so the heat transfer rate is basically mCp delta T. M is the mass flow rate, Cp is the heat capacity, delta T is the temperature difference. So now let's do the analysis. So let's say we have two cases. In case 1, we have constant surface flux. Surface flux is constant. So that means Ts minus Tm is the same. Okay? So T surface of the pipe and the fluid is T inlet. So this difference, there is a difference here after you reach the fully developed region. So let's say inlet temperature here and the surface temperature, this difference is always the same. So this is one idealized situation. You have constant surface flux. This means you have constant surface temperature between the fluid and the pipe wall. Okay? And in this case, if you want to calculate heat transfer rate, so we have H multiplied by delta T. So this is heat transfer rate per area. So now let's go through the analysis here. So this is going to be a lengthy derivation. So let's go through this derivation. Okay, let's go through this derivation. So we have this control volume shown in pink. So we would like to do an energy balance here. Let's do an energy balance for this pink control volume. So we have the convection dq convection is equal to mCp Tm out minus Tm in. So mCp delta T, the energy change in the system, is due to the convective heat transfer coefficient, convective heat transfer. So let's call this as dTm. So if we have a dx, infinitesimally small control volume, so let's call this as dTm for a length of dx. Okay, so that means dq convection is equal to mCp delta Tm, and we stated that in this case we have constant heat flux. So that means dq convection can be written as this constant heat flux, whatever that is, multiplied by the surface area. This is a dA surface. This is constant heat flux is equal to mCp dTm. So we can rearrange this as dTm by dx, constant heat flux multiplied by perimeter divided by mCp. Okay, and in this case so we have this expression here, and if you want to write it down in terms of, if you want to write down this constant heat flux, which is H times T surface minus Tm. Okay, so that is the mean temperature minus surface temperature. If you want to express the, so if you want to write this down as pH T surface minus T mean mCp. Okay, so now if we have a constant heat flux, so that means this term is constant. So this means this is not a function of x. So that means I can simply integrate this. Tm of x is equal to Tm inlet plus heat flux multiplied by perimeter multiplied by mCp x. So this is the variation in temperature with respect to position.